Hope everyone had a good weekend. And so I'm going to talk a little bit about, taking what we discussed last time just a little bit further. In particular, let me see here. Yeah. Okay. All right. Here we go. Now I can hit screen share. All right, so just a quick reminder of what we were talking about last time. So here's a type equation, or sometimes also called the domain equation, which describes the sort of core syntactic elements of row. And then this is a two-level type decomposition. So this ties the recursive knot for row. This shows what you would do to add in built-in processes, values, or capabilities. And then this is a more realistic type. So just to show that, that's the that's about the size of things that one would have to deal with in dealing with the languages, with the complexity of the row calculus. And then we describe the collection types, and then what has to happen in order to go to hang on a second. Where was it? Shoot, where did we go? Oh yeah, right. So we did, I think it was it was on this page. Here it is. So this is the generation of the type of the types for row algorithmically. So just a reminder, this now describes for us the algorithmic generation of a type, which gives us types for row calculus expressions, right? And we can see that this is completely generated. And now let's compare that with something else. So if we consider Abramsky's computational interpretations of linear logic, then he's describing a term language that looks roughly like this. So let me see if I can bring that up 1 second here. All right, so this is the way Abramsky describes terms, the set of terms, linear terms. Now notice that this is actually a function. So it's a function given a set of variables, free variables. Then we'll return the terms generated from that set of free variables. So X is a variable mention in the set of terms that has just the set X. The star is generated from the set of terms from no free variables. And now this is where things start to get interesting and why you had this parameter in the first place. So you have, suppose that T is in the set of terms generated from the set X. and U is in the set of terms generated from the set Y, and further suppose that X intersect Y is empty, then you can form two different terms. One is the tensor, and the other is application. So notice that if we were just using a grammar, right, we would not be able, without this additional capability here, if we were just using a grammar and, you know, a grammar that may be typed, that may have a parametric type values, then we would not be able to distinguish this term from this term from this term. Does that make sense? This is a pair of terms. This is a pair of terms, and that's a pair of terms. Right?
Well,
so
you mean
if
so
you were to code this up as a Scala data type, right? The data type for this is going to have two fields in it, one of which is the T field and the other is the U field. The data type for this one is going to have two terms in it, the T field and the U field, and the data type for this one likewise is going to have the same structure, right? The only thing that distinguishes them is that the tags that you give to those types. So you'll call this one tensor, you'll call this one application, you'll call this one product. Right?
Makes sense.
Right? So the same is going on here. So let me, I'll just screen share the whole desktop. That should be okay. Okay. So the same thing is going here, right? So we've got, you know, tensor and application. Oh, there should be product here as well. I think I'm missing that one.
Oh, this is exactly what you are showing on in the paper, right?
Exactly, right? Now the thing is, so this grammar is not correct in the sense that it does not contain the constraints that are contained in here, right? If you look carefully, this parameter and these side conditions are being used to carefully constrain overlaps of variables, right? So applications and tensors will have no overlapping variables, right? Then moving on, there's an in left, in right, and bang, right? And they're all formed from TX. Here you have the addition of one additional variable. So you get linear abstraction, right? So this is not the same as lambda. This is a linear abstraction. Similarly, you get constraints here for pattern matching and constraints here for case. And so that's going to give you additional constraints on the grammar than what we find here, right? And so if we ignore those constraints for just a moment and we pick, say, list, right, then we'll get exactly the same kind of formula. Now, there are 2 points I want to make. So one thing that Mike and I are looking at carefully is what categorical structure would have the linear lambda, the type level considerations for linear lambda terms. In other words, the formation of these things is like this, right? So the objects of the category would be these kinds of things with the additional constraints, namely the the namespace management constraints, right? So that's something that we're actively investigating right now. Now, to my mind, the solution is relatively straightforward. which is that these are actually dependent types, right? And the dependency is on a set. So the value is a set of free variables. So that's the value that we're using to construct these dependent types. And so the avenue of investigation there is to look at the categorical semantics for either the calculus of constructions or AGDA. So presumably it is possible to code up at the type level, at where you're mixing type and term, where types are built using values as well as types. So in that setting, we should be able to enforce these constraints and get a type level description. And then we can carry forward the exact same algorithm, right? So since I modified this one, I need to add.
So these constraints are not on the value level. They must be on the type level.
On the type level.
When we,
for this approach, right? And in Abramsky's presentation, he's building morphisms, right? These are morphisms in a category. But if you think about it from our perspective, right, if you're going to implement this, right, you want a type level characterization of the terms you can build, right? So this is exactly what you do if you wanted to build Scala types for these terms, right? Right. So that's one. Go ahead. You were going to ask a question.
I'm thinking. You mentioned the reflection last time. So can we use reflection or some macros to accomplish the same?
Possibly. I'd have to think about it. It's not obvious to me immediately. You really need values, right? And so reflection is going to give you types as values, but it's not going to give you values as types.
Okay.
Right. That's the. I mean, it might depends on how you do the reflection. Now the other. Go ahead.
Sorry, I'm thinking as a reflection in a sense that compiler can give us like multiple paths of checking the code. In that way, maybe we can enumerate variables or do these constraints. This is.
Yes, but you want those constraints to be syntactic expressions, right? Over here, he's manipulating it syntactically, right? Right. So I need to be able to have this syntactic apparatus in my type apparatus.
Oh, I see. I see.
So it's a little tricky, but that's sort of the idea. Now the other piece of the puzzle is we'd like our collection here to include linear collections. Now, how do we find linear collections? Now, that's something that's quite interesting. It generates a whole avenue of investigation. So in particular, notice that this really calls out the difference between what Abramsky is doing and what we're doing over here. So what Abramsky is doing, once he has this, then he's going to build up some sequence, right? And the sequence are going to be of the form, on the left-hand side, we've got some variable typing context. And given these assumptions, we can conclude that the term, which is building up these, we're building up a term that uses these variables, has some given type, right? So K inputs, one output, right? And that's what makes it intuitionistic. So at the end of the day, he's going to get a linear logic essentially in the right-hand side, right? So the term all in the right-hand side will have a single term, and that term will be typed using some proposition in linear logic, right? That's so we can think about this in terms of input-output structure. So in that sense, so what Abramsky is forgetting is he's forgetting the term structure in a certain way. Like we see with this, we see a lot more detail at the type level about the term structure. Abramsky only sees input-output relationships, right? So the input side, the input relationships as I'm talking about it are the left-hand side of the sequent, and the output side is the right-hand side of the sequent, right? So if we forget all the interior term structure and just consider the input-output relationships, then this term structure also becomes a data type which gives you the linear container, right? So there's two levels to this, right? There's the type, the term structure as a type, and then the container, right? And what we'd like here is to have linear containers. Well, where would we get one of those, right? How do we define a linear container? Well, one place we can get one of those is to consider these terms, but only we forget a bunch of stuff. Namely, we just look at the input-output relationships. And then these terms model, well, the sequence actually model the input-output relationships, which give us the container. So, so the other way to think about this is you can think about all data structures as sort of something that's sitting between producers and consumers. Like a lot of times in many presentations, especially simply type lambda presentations, or even more sophisticated presentations like Haskell. So the input-output nature is kind of forgotten, right? We forget that a list really needs to sit between a producer and a consumer. It doesn't ever exist outside of that relationship, even at the top level of the Haskell interpreter, right? Or some Lisp interpreter or whatever. A list sits between a producer and a consumer, right? And but a list is not a linear data structure. What we can imagine though is a data structure which has an exact match between ins and outs, right? So so if you think about it as some kind of buffer, where we're placing values, and in order for it to be linear, and in order for it to actually be classically linear, every value that's in the buffer that must also have a pair, which is a producer and a consumer. There has to be. Go ahead.
When you say producer and consumer, I'm thinking about using constructors and then deconstruct.
That's not necessarily the only way to think about it. You could certainly think about row terms as being producers and consumers, right? So there's a buffer between row terms, and the discipline is that whatever is in the buffer has exactly one producer and exactly one consumer. So you could think of R space as such a buffer, yes?
Mm-hmm. Yes.
All right, okay, so that's the idea. R space is a kind of buffer, and the producers and consumers are, that they correspond to the kinds of constraints. And when you have exactly one producer and consumer, then that's the linear constraint. And when you relax that, so you can have say multiple consumers, then that is that's an intuitionistic kind of situation. right? It's more like a functional situation where data values are copied as opposed to used exactly once. And so the, how do you represent that kind of semantic intuition syntactically, right? So that's really the question, is how would I encode that syntactically? Well, one way to encode that syntactically is to use the sequence structure here. So I can use the sequence structure here, and that will give me precisely the data type necessary in order to encode at this level a linear container, and then we can play exactly the same trick, right? So whatever our container grammar is, when we go, so whatever the container grammar is, when we go from there to the type level description, we're going to iterate the container, right? So wherever we had values, we'll now have containers of values, and wherever we had containers of values, we'll have containers of values, right? And then the whole algorithm goes through again as before, right? So we'll get precisely the same, like nothing changes in the generation of this from this, but the relationship of this kind of logic to this logic, right, which is let's see if I have it here. I think he does it maybe above. Here it is, yeah. So this logic is only about the container, right? And this logic says more than just about the container, right? It says something about the structure of the terms that are used to interact with the container. So that's the difference. And this and so because this is Turing complete and this is Turing complete, you expect that you have an encoding of this logic into this logic and this logic into this logic. But this says so much more about term structure than this does. You expect that if you start here, and then you go here, and then you go back to here. In other words, you forget. So from this logic to this logic, that's forgetting, right? We're forgetting a bunch of internal term structure, right? And then we go from here back to here. So now we're freely generating the term structure. We expect that trip around the loop is going to result in a vastly more complex term, right? So you'll get gigantic increase in complexity going around the loop that way. And that should be a way to give us a measure of the expressive power of the two logics. Does that make sense? You understand what I'm saying?
I think I do. Yeah.
So here, just to reiterate, this is a logic that we've algorithmically generated from the model of computation, right? You give us a model of computation and a container, and we're going to algorithmically generate this logic, right? And here's the term structure for that logic. Now this logic allows us, X-ray vision into the term structure. Whereas this logic gives us no such X-ray vision into the term structure. It gives us X-ray vision only into the input-output relationships, but not into the term structure. We can't see nearly as much, right? So when we go from this logic to this logic, what will happen is we're going to forget a bunch of stuff. We're going to forget all of this information about the term structure, right? And we'll only see input-output relations. And then it because we know that both are Turing complete, we'll freely generate term structure that will give us the input-output relationships, right? So just toss in all the term structure necessary to get, the minimal term structure necessary to get those input-output relationships. that will bring us back to this logic, right? But now we've had to add in a bunch of stuff which might not have been present initially, right? Because we knew precisely what terms we were talking about. So we expect that this will result in an explosion of complexity, so again, all of this has to be checked, right? We're in the midst of checking this, but just sort of I wanted to expand on what we talked about last time so that you can see what it looks like with a different example, right? The whole point of working at this level of generality is that we don't just work with Prolang, but you hand us any model of computation and we give you back a type system. So this is an example of another model of computation that has different characteristics, right? So in particular, there's this interesting structure on the terms that is not necessarily easily captured with these kinds of type constructors. And then there's interesting structure in the containers, which is not captured, say, by list. And the question is, how does that perturb the algorithm? In principle, it should not perturb the algorithm at all. It should go through in exactly the same way. But that's what we're going to check next. And part of what we're doing is to identify sort of what's the minimal categorical structure necessary to give us the full range of type languages that we're going to want as a sort of base substrate. All right, that's the whole idea. Any questions, comments, concerns, considerations?
So I want to ask to clarify my understanding. So algorithm of generating with OSLF is basically the same, but when the input language has some linear types or terms, we need to use a different container, and this container must also have some linear characteristics.
You're stating things a little bit more strongly than necessary. So you can the connection between the term language and the container is it's fairly arbitrary. So for example, if we go back to row, right, I don't have to gather the row terms in a list or a tree. Here I'm using a tree, not a list. I could gather them in just a plain old list. I could gather them in sets, or I could gather them in a linear container, right? I could sketch out a linear container here, and then the type system would just use that container, right? The point is that the way we add the container in is completely algorithmically generated, right? Wherever we have a value, right? So here we have a value, right? Here, we're not going to put a value. We're going to replace the mention of the value with a spec for a container of possible values. Right? Does that make sense? And that container could be anything. It could be a set, it could be a tree, it could be a list, it could be a linear container.
How we choose the right container or the minimal container?
There isn't a right container. The point is, it's an input to the algorithm. The algorithm says, you give me a model of computation and you give me a notion of container, and I will hand you back a logic in which the semantics of the formulae are containers of witnesses for the properties of the formula, computations that are witnesses for the properties of the formula. Right?
So it depends what we want as the output.
Yeah, exactly. Precisely.
So what we would get if we take the structure or the language from the Abramsky paper and use very simple container as a set?
Yeah. That's kind of that was what was on this page, right? So we just use a tree here and we'll get this one.
Oh, I see. So you just said that we can do this with a linear container also, but not exclusively, right?
Correct, right.
I see.
Yeah, and using linear containers is interesting, right? It's kind of important, you know, especially if you're maintaining some kind of discipline, like if you have some kind of update discipline on like so again, imagine that your terms, you have some repo of terms, right? And that so in other words, like GitHub, right? So you've got some repository of programs, and now you want to have some kind of update discipline on the repository, right? So in that case, using some kind of updatable structure, it might be linear, it might be more like a SQL database, but
I see.
yeah. So this tells you the semantics of, you know, where, you know, how your terms are stored.
Oh, so basically, if we are using sets, we will not be able to distinguish some terms that maybe we would like to distinguish, right?
You won't be able to distinguish formulae. Your queries will be collapsed. It's not the terms, but the formulae they won't distinguish all situations. Yeah, right. So if you have more sophisticated containers, then your formulae will be more expressive, and that allows you to model different kinds of query semantics.
Okay, that makes sense to me.
Cool.
Can I also ask you about the linear container?
Sure.
It popped up in my head when you were talking about parsimonious lambda calculus, and there were some kind of tracking the variables.
Yep.
Is this very similar?
Very similar. Exactly.
Okay.
Exactly in the same ballpark, right? The basically what he was arguing was that the lambda calculus, so like what he was saying was the terms that Abramsky gets are not ideal for reasoning about complexity style arguments, right? The idea was or the hope, when Girard first discovered linear logic, a lot of people had a hope that, you know, the computational models that we got out of linear logic would allow us to say things about complexity. And to a certain extent, that was true. So Pat Lincoln's PhD thesis, for example, explored some of the complexity characteristics of linear computational models. So in particular, he looked at decorating the bang and the whimper with polynomials, so that, you know, you have some bound on the amount, you have some polynomial that gives you a bound on how often you can reference variables, right? So you could think of that as accessing a storage or updating the storage. So reading and writing to the storage. And so you have some kind of bound on how often you can do that, or how fast the storage can grow, and that gives you some notion of complexity. And the parsimonious lambda guy points out that for certain kinds of expressiveness characteristics, this model of lambda terms is too naive. But if you switch over to a slightly different form, which is his parsimonious lambda calculus, it's still, you know, it's still kind of in the same linear ballpark, but you get much nicer complexity proofs. That was basically his argument, right? So,
I see.
yeah.
Thanks.
Sure. All right. Thank you very much. I appreciate your time and attention, and I will see many of you.
Greg,
yes.
Before we go, Pratyash was asking on Discord regarding your work on behavioral types for Rolang. So I was wondering if there was any research papers or any resources you could recommend to Pratyash to do some investigating on.
Yeah, sure. I'll just show it on the screen here. So this was presented at the Trustworthy Computing conference back in 2005. So here is it's the same row calculus, just silly syntax, and then here is, where is it? Here it is. There we go. There's the behavioral types for, this is namespace logic, and this logic comes from running this algorithm.
Great.
So you see that, you know, there's row, there's the namespace logic. And what the paper doesn't say is that there's an algorithm that generates this logic. It just describes the logic. I mean, you know, I was preparing to, you know, this was a little example, right? And the point is that the logic is super highly expressive. There are things that you can say in this logic that are pretty awesome. Like
Sure.
you can give, you know, compile time firewalls as one example of being able to do this kind of, you know, what you can do with this logic, the expressive power of this logic. Compile time firewalls are pretty awesome, right?
Mm-hmm.
You know, it's like firewall technology is, you know, hundreds of billions of dollars, and we can eliminate firewall technology in favor of compilers. You know, I mean, I'm exaggerating a little bit, but I think you get the point.
If you could, real quick, if you could just copy and paste that link in the chat, I'm going to put it in Discord for others as well.
Yeah, sure. I mean, it's on our page, but
yeah, well, yeah.
It's on the Archain research page, but
Okay.
I put it in the chat. Yeah, I'll stop screen sharing.
I wonder if Pratyush wants to introduce himself and say a little bit about his background and what he's working on.
He did that at the beginning, but
oh, he did. Okay.
Maybe he wants to say some more.
Yeah, I'm a student of physics. I'm doing my PhD. I got interested in the computational problems very recently, like a couple of months and so on. And I've been looking at different approaches to blockchain. When I discovered Rolang, I really liked the approach, which is when I started pursuing. And it's a very new language to me. So like, I want to learn the language, and that is why like I'm sort of following these discussions and so on.
Yeah,
Cool.
Very good. So feel free to, we're happy to answer any questions you have. I do have a question I wanted to, not related to OSLF, but I was generally, I wanted to, I don't know if we have the time. I think we have a few minutes maybe.
Yeah, we do.
The indexing in the chain, I was wondering, is it possible to do something with, at the application development time, somebody can say, you know, these are the things that I need indexed, and then we can just carry the index through, or is that too complicated to,
I mean,
the wrong way to do it?
there are a lot of different possible designs. I mean, we're gonna, it's the usual thing where we're gonna have to hash out what we think are the most usable ways to do that. It's not, you know, it's, how do I say this? The surface area of these kinds of things is often where one spends like gobs and gobs of development time. So as an example, you know, we all kind of get the principles of arithmetic. But at the end of the day, the design of real arithmetic in a programming language is non-trivial because you have all of these edge cases, right? And it's like you have integer overflow and divide by 0 and how you want to handle errors like that. That are non-trivial, and they take a lot of time to get right to the point where it's usable in a wide range of cases. And the same is true for these kinds. I'm using that as an analogy for, you know, what we're going to have to go through when we talk about, you know, providing search on the ground types, right? So we know how to do basic pattern matching, but when you're talking about exact equality, you know, for the ground types, then you have to be, you know, you have to be careful because there are ways to run afoul of those of those kinds of computations, as everybody knows, right? And that's what makes databases hard. So there's one of the things that makes databases hard. So it's not like, I mean, to the best of my knowledge, I mean, maybe there's some really cool rocket science that makes all of that complexity simple. But to the best of my knowledge, most of that is you know, hard-won experience. And you know, it's complexity that you just kind of have to go in and hack your way through, as opposed to having a really nice, clean architectural mathematical solution.
I mean, is equality the only one that's the most complicated? For example, instead of equality, can we offer contains as a cheap and easy way to do it? Or
no, it's not cheap and easy. You still have to worry about, you know, if you're searching gigantic sets of these things, you still have to worry about indexing and stuff like that. So no, it's not. There's no silver bullet here.
All right, sounds good. Okay, I'll just then I guess we'll have conversation in the. I mean, what I would like to do is put some thinking in that space, and then put some either designs or plans. At least begin to think about designs, I suppose. And of course, we do need to think about, in the relative scheme of things, how important is it? Or are there workarounds, in which case maybe we don't have to worry about that problem for now, but that's something to explore.
Yeah, no, I agree. I think, you know, as I've tried to say, that most of that needs to be customer driven, right? So we get a bunch of customers and they kind of say, well, this is what we need. Because, you know, you could spend decades tinkering to, you know, but without good, strong customer feedback, you know, it's hard to know which amongst, you know, several thousands of designs are going to be the most usable.
Right. Right. I mean, you know, I'm completely for market-driven development. So
yeah, exactly.
So,
yeah.
All right, very good. So we'll take it.
Greg, can I just ask you, related to that, are you thinking about some special way where a match is extended, or some kind of syntactic addition to Roland, when we can say, like very similar how in SQL you're basically saying I want to index this column. Like,
yes. Yeah, exactly.
Okay.
That's precisely the idea. So we should be able to extend on the syntactic side. We should be able to give some indication as to what matching needs to be indexed. And then on the semantic side, we need to be able to generate those indexes, you know, in a reasonable fashion.
I see.
Yeah. Coolio. All right. So I'll see everyone in about 10 minutes. Thanks all.
All right,
Thanks.
thanks to you.
Sure.